Hello all. So up to now, we have been discussed about the non-isolated DC-DC converters. So in that there we discussed about the buck converter and also the boost converter that we have discussed in those non-isolated DC-DC converter. So now why we are going for the isolated DC-DC converter that we will discuss, and then we'll moving on to the isolated DC-DC converters. Right. So in the non-isolated, as we know that in non-isolated DC-DC converter, so you know that input and output shares the common ground. Input and output shares the common ground here. Okay. Now let us assume any if any uh, circulation current in the input and output side, if any circulation currents in input and output, for example, so if any circulation current in the output side, so that circulation current will affect in the input side since the input and output having a common ground. If any circulation currents in the input side, that will also affect on the output side since it is having a common ground. So this circulation currents will create some disturbances in the input and output side. And because of this circulation current, so the operation is not safe. Operation is not safe with the non-isolated. Operation is not safe. Okay, so because of this, and so when they are working for few watt levels, okay, when they are working for few kilowatt levels in that range, so there are the possibility of the circulation currents are more, so thereby it will create more disturbances. Okay, so in that it may cause the a not safe operation. Okay, right. Now the first point is because of the circulation current, the operation is not same. That's why it is limited to very few kilovolts. Okay. Now, what is the gain now? Okay, when you are talking about the non-isolated, what is the gain? Okay, so the gain is limited for the case of the non-isolated. The gain is limited. What is this? Okay, for example, you have a 24-volt source. You have a 24-volt source. Okay, now you wanted to convert into 2 volts. That means you are doing a buck operation. You are using a buck converter to convert the 24 volts to 2 volts. So now it will be, what is the gain in this case here? Gain is equal to output by input 12 by 24. So which will create 1 by 12 times 1 by 12. Okay. So this is a very, very small gain. Okay. Small gain. Okay. So this is 1 by 12 is a very small gain. It is difficult to obtain from the non-isolated converter. It is difficult to obtain. It is difficult to obtain from non-isolated converters. Okay, let me take similarly here. We have discussed about buck converter, right? Now you have a 5-volt supply or 5-volt source. Now you have to convert into 100 volts. Okay, so you are doing a boost operation, boost converter you are using here. You are stepping up. So if we talk about the gain here, so it is output by 100 by 5 is, so it is the 1:20 ratio here. Okay, here also such very high, this gain has a it is also very high gain. It is also not or difficult to get the gain. Okay, So this there's a possibility of small gain is also not a possible. The 1:20 ratio gain is also not possible to achieve by the use of the non-isolated DC-DC converter. Okay. Now here, what is uh, the gain that can be able to get from the uh, non-isolated DC-DC converters? So here we can obtain the uh, best gain can be achieved from non-isolated DC-DC converters. Okay, if I talk about buck converter, so we could able to get a 1/2 gain. Okay, and if we talk about the boost converter, so we will be able to get a 2. Okay, that means so if for example you have a 24 volts, so that means you can able to get the you can able to get the secondary voltage up to 12. Okay. Similarly, if you have 5 volts, and we can able to boost up to uh, 10 ohms. Okay, so in that range only it is possible by using non-isolated DC-DC converter. Okay, so this drawback, the gain drawback here in the non-isolated can be overcome by using isolated DC-DC converter. Okay, so here in the isolated DC-DC converter, what is extra that we have is intervening transformer. Intervening transformer. Intervening transformer. So that intervening transformer with turns ratio can be able to get for can be able to achieve for the large gains. Okay, the intervening transformer with the turns ratio, we will be able to obtain large gains. Large gains. Okay, so that is a major advantage here. Okay, now if we talk about the isolated DC-DC converter is a converter with intervening transformer. That converter can be called as isolated DC-DC converter topology. Okay, so if I want to define here a converter with intervening transformer, a converter with intervening transformer, so that can be called as, that converter can be called as isolated DC-DC converter, DC to DC converter topology. Okay. Now here in this converter, we are going to have high frequency transformer here. Okay. So in this intervening transformer I said, right? So here that transformer is a high frequency transformer. High frequency transformer. Okay. Now what is advantage with the high frequency transformer? Okay. As the frequency increases, okay. So what is the size of transformer? What is the size of transformer? And then when the size of the transformer decides the size of converter. Okay. So now as the frequency increases, the size of the transformer can be reduced. Thereby, the size of converter also can be reduced. So because of this reducing size, so the total converter size also will be reduced. Okay. So we can call this one as miniaturization of transformer. Miniaturize of transformer will also miniaturize the size of converter. Will also miniaturize the converter. Okay. Will also miniaturize of transformer and converter. So both are miniaturized. Okay. So we will see an example here how this will be miniaturized. Okay. How the size of transformer is going to be reduced. So by taking an example of RPS here. Okay. So as we all know that we have a regulated power supply RPS in our laboratory, right? So that RPS assume that it is having a 15 volts power supply, 15 volts power supply. Okay. So now you know that what is RPS at the output we are going to get DC, right? So what is the input that we are giving for that is uh, uh, 230 volts AC, 50 hertz frequency, right? So that we are giving here. Okay. Now here we will be having a transformer. This transformer will step down the voltage. Will step down the voltage. The input voltage here is 230. So this 230 volts can be stepped down to 20 volts. Okay. So this step down voltage is given to the step down voltage 20 volts is given to a rectifier. Is a rectifier because we have to convert it, right? So now if you talk about the input of the rectifier, we are going to get a current here. This current is a peaky waveform. Okay. So peaky waveform. So this is not a pure sinusoidal. Peaky current waveform. Peaky current waveform. This is not a pure sinusoidal. Okay. To make it a pure sinusoidal, so we have to involve a circuit in the rectifier called as power factor correction circuit. Okay. Power factor correction circuit. Okay. So this power factor correction circuit can make this as a pure sinusoidal. It will make sinusoidal. Now, the secondary side of the rectifier we are going to get as a DC. Now, we are going to use a capacitor here. So to reduce we are going to use a capacitor to reduce voltage ripples or oscillations, to reduce voltage ripples or oscillations. Now here, now with this capacitor is a we can call it as a bulky capacitor, bulky electrolyte capacitor, bulky electrolyte capacitor, electrolytic capacitor. So because of this capacitor, this bulky capacitor, there is an issue of reliability. So reliability issues will occur here. Reliability issues is an issue with this. Reliability is an issue. Okay. So this is about the capacitor that we are using here. Now this voltage, whatever the DC voltage that we are going to get here, that we are giving to a regulate voltage regulator circuit, voltage regulator circuit, voltage regulator circuit. Okay. So in this voltage regulator circuit, what it will be there here is, so we used to have a 7805 IC, 7805 IC. So this will having a plus 5 volts voltage drop here. Okay. Now the output voltage that we are going to get is finally a regulated voltage, regulated output. Okay. So here we have this. Okay. Now, so because as we are using the ICs right here, so because of these ICs, so we have a different ICs that we are being using. So here, so the input voltage that we are giving is 20 volts, and that 20 volts is given drop to 15 volts, and the 5 volts is going to the other old 5 volts is going to be. I mean, we are going to get the what is that 5 volts is the output, and this 15 volts we are going to be dropped. Okay. So similarly, we have a different types of ICs here. 7805 IC. So this will have a voltage of 5 volts here, and 7905 IC. So this will have a positive and a negative voltage of 5 volts. You can be able to get it. And 7815 IC, and it can able to get a 15 plus 15 volts. And next one we have a 7915 IC. So it's been able to get a minus 15 volts. The output. Okay, these are different ICs here. Okay, so right, as we know that the input we are giving is 20 volts, and the 15 voltage will be dropped here, and finally at the regulated the output side, uh, 5 volts we are going to get at the regulator. 5 volts at regulator we are going to get, right. So this, if you observe here, what is the drop power loss is huge power loss, right? You gave it 50, 20, 15 volts dropped and 5 volts you are going to get output. So that will create a huge power loss, huge power loss. So when the power loss is used, as you know that heat will be, so the circuit will be heated up, right? So heat will be more, with that one heat, circuit heated up. So that when the circuit heated up, we have to dissipate the heat, right? So to dissipate the heat, what we required a big heat sink, right? A big heat sink. So this big heat sink can dissipate the heat. Okay, so the big heat sink is required. As you know that as the heat sink is big here, so what will happen? The size of the heat sink will be more, and thereby total converter size also will be more. Okay, so if you observe in the laboratory, so we have the voltage regulator. Those regulators have uh, a very big size. Okay. Now I wanted to comment like this here. So as you know, the voltage is proportional to voltage. Okay. Voltage is proportional to frequency into flux. Okay. So if I take voltage for frequency ratio, it is proportional to flux. Okay. So now if you take as frequency increases, so flux. Okay, so let me take it as frequency decreases. We will take it as frequency decreases here. So flux, what will happen? The flux here, flux will improve. So that improved flux will also improve the Bmax. So as the Bmax increases, so we need to set up that Bmax, a huge Bmax. So we have to choose large cross sectional core of transformer. Okay, so as the large cross section area of the core increases, thereby size also will be more. Okay, so now I am talking about here that as frequency is less here, so the flux it requires more, and to set up the flux, we need to choose a Bmax value which is huge. Further, to set up the huge Bmax value, we have to take the cross section area of the core of the transformer is more. So because of this, the size will be more. And also here, because of this regulator IC, so it is dropping more voltage here. Because of that, there will be a huge power loss thereby. So we did a big heat sink to dissipate that heat. So that because of that also, so here we have a size of the converter will be more. Okay. Now this can be this drawback, whatever the drawback is there with this frequency and also the size of the heatsink can be uh, overcome with the other one called as SMPS. What is that SMPS? Switched mode power supply. Switched mode power supply. Switched mode power supply. So in short, we call this SMPS. SMPS. So here in this switched mode power supply, we use a high frequency transformer. We use high frequency transformer. So where this high frequency transformer size will be size of the converter will be very small. Okay, size of the converter will be very small here. Okay, now we'll take the same example. So how we take the converter here? The input of the converter is again here 230 volts, 230, 50 hertz. So that is a single phase supply. Okay, now this is given to earlier. when we discussing about this one here RPS, we have given to a step down transformer. Now we are not going to give a step down transformer directly. We are giving to the rectifier. We are going to give to the rectifier. So rectifier. Okay. So this rectifier convert the AC to DC here. So that DC, we are going to get a DC here. This is a plus and minus. Okay. Now this DC, we are going to give to the a DC converter, a DC to DC converter, DC to DC converter. Okay. Now, so here in the secondary side here, we are going to get the required DC at the output, that is assume that 5 volts. We required 5 volts. Okay. Now here, where is the part of the isolate here? Now come to the picture here. Now if you take it as an input is a 230 volts, what is the voltage here at this point after the rectifier is? So it would be 230 times of root 2. Okay. So if we take the maximum value here, because of the DC here, average value can also call it as. So here, the peak value we are going to get this DC converter is around 325 volts. Okay. Now what will be there in this DC converter? Okay. So in this DC converter, so first we will have input is DC, right? So that DC we are going to convert into AC here again. So that is DC to AC. Okay. So with a high frequency, we are going to convert DC input is there here, the DC here. So this DC are going to convert with the AC with high frequency. The high frequency. This signal we are going to give to the high frequency transformer. Going to give to the high frequency transformer. So this high frequency transformer is given like this here. This is a high frequency transformer. In this one, we are going to have 2 secondary windings. So because we can take any number of secondary windings in the transformer secondary. Okay. Now here the advantage with this one is I can able to take 5 volts here, the one winding of the secondary, and I can take the remaining voltage 15 volts here. Okay. So I can convert this to one rectifier. So rectifier 1, and I'll be giving to this to a rectifier 2. Rectifier 2. Okay. Now I'll be having a different application here. I have some different applications, like if I want to connect a 5 volts here, so from this I can give to 5 volts. If I want to get 15 volts from this, I can able to get 15 volts like this. Okay. So there is a possibility of reverse voltage in this case also. Reverse voltage also possible. Reverse voltage also possible with the transformer windings. Okay. Now if you observe, the observation you must have is, so what is the frequency here? We are not talking about the after the conversion. There is no question of there is no concept of 58 transformer. Okay. 58 transformer is not there here, and there is no regulated IC, no regulated IC. Okay. So because of this, so there will be a no 58 transformer. There is no regulated IC, so that overall the SMPS size will be miniaturized. SMPS size, okay, miniaturized. So that's why if you observe here, the RPS which are available in the lab is very huge size compared to the SMPS that we are using in the personal computers. Okay, so SMPS, because of this SMPS miniaturized, because of the all features. Okay, now where we are using this, the application of this DC-DC converters in the electric vehicles. Okay, up to now we discussed about the application where we use. Now in EV vehicles. Okay. So for example, I want the auxiliary loads like auxiliary loads. Okay, like lightning, auxiliary loads, lightning, information, and entertainments like so ventilation and heating, okay, and AC systems and different ECUs. Okay, so these all are will have the auxiliary supply of 5 volts and apart from the battery charges, right? So if it in the electric vehicle, the charging voltage of the battery is different than the auxiliary loads. Okay, so to get the different voltage levels, it is very easy with the isolated transformer because this one we can give to the directly to the all auxiliary loads, and this one we can give to the charging perspectives. Okay, and if you talk about the battery charges here in the electric vehicles, battery charges or battery chargers here. So we have a different types of battery chargers. One is onboard chargers, onboard chargers. Next one is off-board chargers, off-board chargers, and third one is wireless chargers. Okay, so in these three cases, we are going to use these isolated DC-DC converters. So these onboard and offboard charges can be obtained with the dual active bridge converters, DAB, dual active bridge converters. So these dual active bridge converters are used in this onboard and offboard chargers. Okay. So onboard means so complete charger converters and all can be used in the vehicle itself. Okay. Some part of the converter is at the charging circuit of out of the vehicle, and some of the converters are there in the vehicle. So that is outboard charges. As you know, wireless charges. So without wires, so how we can charge a vehicle? These are wireless chargers. Okay. Now, if you come to the what are the different types of the isolated DC-DC converters? Okay. What are different types of isolated DC-DC converters here? First, okay. So types of here. So first, we will have a flyback converter, and next we'll have half bridge converter, and we have full bridge converter, and we also have fourth one dual active bridge converters, and fifth one forward converters, and the sixth one we have a push pull converters. Push pull converters. Okay, so these are different classifications that we have in the isolated DC-DC converters. So these are classifications of isolated DC to DC converter. Okay. So now we come to the flyback converter here. So it can be used less than 100 watts. And if we talk to the half bridge converters, so uh, less than so it is 50 watts. You can take it as half bridge less than 50 watts. So it is generally we have SMPS, right? SMPS for PCs. All those we are using this half bridge here. And if you talk about full bridge, so the best example in our solar PV systems, and we also have some large power supplies like large power supplies like welding. So in the weldings we are going to use, and some telecoms towers, there we are going to use telecom towers, full bridge, and the range of the power is in terms of 100 watts to few tens of kilowatts, few tens of kilowatts. So this is the range of the full bridge converter. Okay. And if we talk about the dual active bridge converters, these are used for very high power rating, very high power rating. And we also have a forward converters and push-pull converters. Now, out of these all the classifications, so we have in the syllabus we have a forward converters are there, and full bridge converter are also there. Okay, so first we'll discuss about forward converters and full bridge converter as a part of syllabus. Then we will also move to the resonance converters. Resonance converters. Okay. So these are the techniques of soft switchings. Okay. So first we will discuss about the forward converter. Okay. The first topic in the isolated converters are forward converters. Okay. So these forward converters are quite like buck converters. Okay. It's quite like a buck converters. So I'll just take about the buck converter cycle, like from how we brought up the forward converters from the buck that I am going to take in the right. So if you see this circuit here, so this is a buck converter that we have discussed. So the input supply, like the switch, and these are the buck converter circuit that we have. How this buck converter circuit is molded as a forward converter. The input source is same here, and we are going to have the high frequency transformer, and we have a switch, and then we have a diode D2. We have kept an extra here, and this converter circuit we have kept as this here it is. Okay, forward converters. Okay, and in the output side, we have a like R naught is there, L naught is there here, R naught, L naught, and D1. So which are identical to the buck converters operation. Okay, so which are same as the buck converters here. Okay, and if you observe here, so we have a Q. Okay, Q is a switch here. So this is a switch Q. So we have kept here. Now this switch can be this Q switch is a kept can be kept at the positive terminal. Like if you take a transformer here, this is a positive terminal of the transformer. This is a negative terminal of the transformer. Okay, so we can keep the switch in the both the sides, like you can like positive terminal or at the negative terminal. So it does not have any issues here. In this case here, the switch, the Q can be placed in the positive terminal of the transformer and the input supply, or between the negative terminal and DC link. Okay, this is called as DC link. Okay, link. DC return we can call it as. Okay, but however, so we can place it the two ways, right? Either it's take up at the positive terminal or the negative terminals. Okay, it is quite an advantage to keep the switch between negative terminal and the DC return because the control of the switch is very simple here. The control of the switch is very simple and to implement it is okay. It is better to keep the Q at the negative terminal to the DC return. Okay, so it is having a is easy control and it is easy to implement. And uh, this the access also very easy right here between the negative terminal to the ground. It's easy. Okay. Now, if talk about the D2 here, so we have additional. We can call it D2 is an additional diode from the buck converter to ensure when transformer. I mean to ensure that when the primary side of the switch is conducting, then only the D2 is going to connect here. Okay, to ensure the primary side of the switch Q is conducting or not. Okay, then that is the purpose of this. Okay, when Q is conducting, then only D2 is going to conduct. Okay, so that is the purpose of the D2 here. Okay, now the question is that here is this transformer, now we come to the transformer, is this transformer is magnetized or not? Okay, so in order to operate the transformer or in order to give a mutual induction principle here, the transformer must be magnetized. Transformer must be magnetized. But how to get this magnetized directly here? Okay, so to get the magnetization, okay, so we need to have a circuit, or we need to have an extra uh, winding in the input side here. We need to have extra winding in the input side. Okay, so that extra winding is going to magnetize the primary winding. So then once the primary winding is magnetized, so that converter is going to the transformer is going to work under the mutual induction principle here. Okay, so if you look at this here, observe here the primary winding in this the primary winding here this primary winding, and here also we have a primary winding. The extra winding is called as the territorial winding, or it is also called as magnetization winding. Okay, it is also called as magnetization winding. Okay, so the purpose of this winding is to magnetize the transformer, to magnetize it. Okay, to magnetize the transformer. Okay, now right now, once you magnetize it, so we have to demagnetization also. We have to do the demagnetization. Okay, right. For that case, we have kept a diode here. So this diode D3, what the purpose of D3 is? Okay, so it makes sure that for every cycle for every cycle, uh, the inductance must be demagnetization, so that the primary side of the whenever the primary side of the switch is not connecting. Okay, so right here. So what I mean to say here that, so the purpose of this the winding is NT here. It is used to magnetize it. Okay. When the switch is conducting, it has to magnetize. Okay. When the switch Q is not conducting, the transformer winding must be demagnetized. Demagnetized. Okay. So this can be done by the diode D3. Okay. When the switch Q is not conducting, so in that cycle, the transformer winding must be demagnetized to avoid the saturation. Okay, avoid the saturation. So the third winding, the purpose is for magnetization. Okay, so which is having an NT number of turns, and the purpose of diode D3 is to demagnetize the winding when the switch stop conducting. Okay, and here because of this magnetization of the magnetizing winding, the primary side, so the duty cycle delimited to a certain value, or the primary winding duty cycle is limited. Okay, because of the extra winding. Okay, so typically the duty cycle of the uh, primary winding, the maximum duty cycle of the primary winding, typically it is 0.5. Okay, so it cannot possible. The maximum beyond 0.5 is not possible, not feasible also. So with this structure, okay. Now, if you look at this here, we have for a buck converter, we have simply an input source and the converter, right? But instead of that, we have LS and C1. Okay. So for time being, for simplicity, the source inductance and the filter capacitor C1 can be neglected for simplicity. So directly the input voltage is going to apply across the transformer. So that is the one assumption. Assume that the source inductance and the filter capacitor C1 can be neglected for simplicity. Okay. Now, if you come to the operation here, there are three modes of operation. Operation here. There are three modes of operation here. First mode here, when Q on here, when the switch Q on, so how it will react or how the circuit is works. So here, when Q is on, okay, when the Q is on here, this Q on. So what happens here? So when the Q on, so the primary winding is magnetized. The winding is magnetized, so that when the winding is magnetized, the current IM is also flowing. The magnetizing current is flowing because of the magnetized inductance. Its inductance is magnetized. Okay, so that in reflect this one, the flux is linking with the secondary winding, so that the secondary winding current is also flowing IS by the transformer action. Okay, and uh, now in this case here, when this magnetized here, there is no current is flowing through the territory winding when the switch Q is closed. Okay, and the diode D1 is in the reverse bias. That means it does not conducting, and it means it will in the reverse bias. Okay, now so in the mode one or of switch mode one here, so we are Q is on, so that the winding is magnetized here. So when the winding is magnetized, okay, so the IM is also flowing thereby. So with the transformer action, secondary current is flowing. So this D2 is in the forward bias. So current is flowing to the loads like this. Okay. In this case here, the diode D1 is in the reverse bias. It's not conducting, and there is no current is also flowing to the terminal winding. So this D3 is in the reverse bias because it is in the magnetizing mode. Okay. Right. Now this is about the mode 1. Okay. So if we talk about mode 2 here, so how in the mode 2 is acting here. Now in this mode 2, I'll just simply turn off the switch. Okay. Simply turn off the switch here. So how this circuit is look like here. So this is the circuit when in the mode 2. Okay. So this is the circuit here. Okay. Right. When switch second mode here, when the circuit in the second mode of operation, the switch Q is in open circuited, the switch is open. When the switch is open, so automatically the Q is not conducting, Q open is not conducting. So there is no there is no conduction in the primary side here. But however, there is some amount of energy stored in the inductor here. So because of the energy stored in the inductor, and so that energy, okay, because of the energy, still there is a current is flowing here. There is a flux. We can call it as there is a current is also flowing in the transformer to the secondary side. Okay, and then now switch is not connecting. Then immediately the D3 is coming to the picture. So this D3 is going to be turned on to make it reverse bias. This is in a forward bias, right? This is in a forward bias to make its demagnetization of the transformer, demagnetization of the transformer. Okay, so because of this energy stored in the inductor, still some amount of current is flowing here. Okay, but here, so some amount of current, and here this one, in this one here. But the problem here is when the current is flowing, the moment the Q is off, when the Q is open here, so automatically the D2 is off. Okay, so this D2 will be in the reverse bias. Okay, so reverse bias. Okay, the energy, whatever it is there in the transformer, can be demagnetized by the diode D3. So it will be demagnetized. Now it's fine now. Okay, but there also some amount of energy stored in this inductor, right? L naught. Okay, so during the normal operation, so this will be act like a positive and negative here. But during when the Q is off, this D2 will be in the open circuit. Now this inductor L naught will maintain the current direction is same, but it will change its polarities. It will change its polarities like plus and minus. Okay, so because of these polarities, the diode D1 will be in the forward bias. So the current which is flowing here, it will maintain or it will circulate in this path. The current will maintain in this path. Okay, so in this first and second case, the current flowing through the load is maintained as the same here. Continuous current is flowing here, so that the load current is in the continuous conduction mode operation. Okay, so I repeat the secondary here. When the Q is off, the mode 2, when the Q switch is open, so thereby the energies in the transformer can be demagnetized by D3. The D3 is come to the forward bias, so it will be demagnetized. Now then, the moment when the DQ is off here, D2 will be off. The energy stored in the inductor will can supply the current through the load in the same direction of current by changing its voltage polarities. Thereby, the diode D1 is come to the forward bias, so that the current will maintain in the same direction. Okay, through L naught and R naught and the through D1. Okay, this is the mode 2 operation. Now come to the mode 3 operation. In this mode 3, so in this mode 3, there will not be any current in the transformer primary and secondary. In this mode 3 here, there will not be any current in the transformer primary and secondary. Look at this here. So here the Q is off, Q open, and diode D is also demagnetized. Okay, there is no current here. No current here. Current IP is 0, and this I total current is winding current also 0, and here also current is 0, and this D2 also in the reverse bias. So here up to this part there is no current. But here, what are the energy stored in the inductor here? So because of this energy stored in inductor, it will maintain the current direction like this. Okay, it will maintain the current direction in the same. Okay, through diode. So still the current is flowing through diode D1. D1 is going to be forward bias. Okay, so these are the three different modes of operations in SCR. Okay, now we will see that what is the duty cycle. Okay, so as you know, continuous conduction, we have taken that continuous currents in the forward converter. So in the forward converter. Okay, so now as we know, with this forward converter which we have taken from the buck converter. Okay, so if we just look at the buck converter output voltage equation, so V output is equal to D times of V input. Okay, so in this buck converter there is no transformer. Okay, but in the forward converter, what is there? In the forward converter, we have a transformer. So when the transformer is there, so we have to include the primary winding turns and the secondary winding turns. Okay, so if we take D here, V output by V input. Okay, now if we take the same D value for the forward converter here, the D value D is equal to V output. Okay, so how much secondary turns are there here? Okay, V output by NS and V input divided by how many number of primary turns. Okay, so that 1 by N times of V output by V input, V input here. So we can take it as a input V1, no problem. And so what is N here? Where N is nothing but N is equal to the transformer turns ratio. Okay, turns ratio of transformer. So it would be NS by N. Okay, so this is the duty cycle equation here. Now, if we discuss about the what is the output waveforms? Okay, output waveforms for a forward converter. Output waveforms for forward converter. Okay, right. So now when the operation is similar to the buck converter, the waveforms are also more or less the same as the buck converter here, T, and this will be on time. This will be on time. And this would be off time. Okay. So right. So I'll be calling this as D into TS, where TS is the switching frequency. That is on time. It is 1 minus times of D into TS of time. So totally TS switching time here. Okay. And so we can call this equation is voltage across inductor VL naught, VL naught or VL decade anyway. Right. So now earlier we have in the buck converters. So we have a peak to peak current. We have analyzed there, and we also in this one we have a parasitic, so like a LS and a C naught. We have neglected. Okay. Now, so what is the inductor current? Delta IL. So delta IL naught, right? This is a maximum current, right? So this is about the voltage across the inductor. Now, what is the current through inductor? Okay. Now, current through inductor. So it will start at the point here, somewhere else here. So during the on time, the inductor current is increasing, and during the off time, the current is getting fall, and again during the on time, the current is keep on rising. So it will continuously varying here. So the average current of this one will give the load current which is flowing here, the I naught. Okay. So from this, if I want to find out what is the peak to peak value of delta I naught. Okay, delta I naught peak to peak means which value? So here we can take this value. Okay, so this is a negative peak here and this is a positive peak. This value we call this as delta IL not peak to peak. Okay, and this we'll call this the minimum value, right? Delta IL not minimum, and this will call as delta, or you can call IL not maximum. Okay, IL not maximum, IL not minimum. So this is the change value, right? That's why I've taken a delta IL not peak to peak. Okay, now what is the delta IL not peak to peak? Okay, so as you know from the inductor current formula, 1 by L naught into N times of input V1 minus V output into D times of Ts. Okay, this on period, right? So as we already discussed about this equation, how we got this. Okay. Now, during the, like we have taken it in terms of D into Ts, right? So if I want to take delta L naught peak to peak in the duration of 1 minus during 1 minus D into Ts time duration. Okay, so this is about D into Ts duration. And if I talk about 1 minus D times of ds here, so delta IL naught peak to peak, so that is equal to V naught into 1 minus D times of Ts divided by L naught. Okay, so this is the peak to peak current during the off period. Okay, I mean 1 minus D times of Ts. Okay, now what are the now if we equate these two expressions here, we are going to get the one expression like whenever you want to get the formulas here. So equate these two. If I equate these two here, we'll be getting delta IL naught peak to peak. So is equal to 1 by L naught into N into V1 minus V naught into D times of Ts, and that is also equal to V into 1 minus D times of Ts divided by L naught. So this is the expression. So wherever you want to get the peak to peak for the both intervals like on d into ts and also like 1 minus d times of ts. Okay. So solving these two equations, we are going to get the relationship between duty cycle and also voltage gain. Okay. To get uh, duty cycle and voltage gain. Okay. Now, as we know that, so we have a D2 is red when the when switch Q is on in the primary side and D2 is also conducting, right? So when the D2 is conducting, there is a current, secondary current is flowing here. So what is the current? Okay, secondary minimum current. What is the secondary maximum current? Okay, so as D2 is conducting the secondary, so when the D2, like this circuit, and D2 is conducting here, so there will be a secondary current is flowing. So, okay, current is flowing in secondary current is flows here. So when the current flows here, what will be the minimum IS minimum current and what is the IS secondary maximum current? Okay, or a cycle here. Okay, so this IS minimum is also equal to IL not minimum. Okay, current flow into the inductor in the minimum here. So that is equal to initially. So if it, as we remember, so what is IL minimum for the case of the buck converter here? IL not plus delta IL by 2. So that we discussed here. This is a for buck converter. And if you want to get the IL max formula here, I naught, so this is about IL max, it is I naught plus. If you want to get the IL minimum, okay, so I naught minus delta IL by 2. Okay, so these are two formulas for buck converters. Okay, now similarly, if I use those formulas for this, solve this here, I naught minus delta IL naught peak to peak divided by 2 here. Okay, so if I talk about the maximum IL IS maximum, so this would be IL naught maximum. So this would be I naught plus delta IL naught peak to peak divided by 2. Okay, so now these are the two currents in the secondary two currents. Okay, normally. Now we have a transformer right here. Okay, if any current is changing in the primary, will affect in the secondary. Okay, because of the mutual induction, right? If any second current in the change in the secondary current will also reflected in the primary side. Okay, now the secondary current is reflected to the primary side. Okay, the secondary current, secondary current is reflected to primary. So we are using involving the transformer. The secondary current reflect to the primary IS dash, I will call it as N times of IS. Okay, which is IS dash is equal to N times of IS, where N is turns ratio. Okay, transformer turns ratio. Similarly, so we also have the minimum and also maximum currents in this reflected secondary current, right? So when call this minimum and maximum reflected secondary currents IS minimum and IS maximum. Okay, so IS minimum dash, we call it as reflected, right? Dash, we'll take it as N times of IS minimum. Okay, so if I want to get the IS maximum here, IS maximum, IS max dash, that is equal to N times of IS max. Okay, so just you have to multiply with the turns ratio of the transformer. Okay, So now this is about the secondary currents, minimum and maximums, and reflected secondary currents, minimum and maximums. Now we are in the primary side. We also have a what is that magnetizing current, right? Okay, with the magnetizing current. So during the period D into Ts, okay, what is the voltage plus inductance is V1, right? Okay, voltage plus inductance is V1. What is the voltage across the magnetizing inductance? Voltage across magnetizing inductance. Okay, so I'll call this well VLM, voltage plus magnetizing inductance. VLM is equal to LM times of DIM by dt. Okay, so what is DIM is? So that is magnetizing current. Okay, voltage across magnetizing inductance is equal to Lm times of DIM by dt, or it is also written as uh, so VLM is voltage across like input, right? So that is input voltage and inductor voltage across inductor and primary and same because we assume that LF and capacitor is neglected here. So this DIM, instead of this DIM, I'll call this IM peak, magnetizing peak current divided by the D times of TS. So this is also one more equation. So if I write this 1 by Ts, it will comes into the frequency. So switching frequency into Lm, Im peak divided by D. Okay, so this is the expression in terms of input voltage and switching frequency and duty cycle. Okay, so as we know that the magnetizing current, initially there is no magnetizing current, so it starts from 0 to the peak value of magnetizing current. Okay, so what is the peak value of magnetizing current? So peak, Im peak is equal to D times of V1 divided by switching frequency into Lm. Okay, peak value of switching the magnetizing current. Okay, now what is the minimum, maximum, primary, and tertiary currents? Okay, so what is the minimum and maximum primary currents? Okay, so I'm talking about primary currents. Okay, so for the minimum current, so directly, so for the minimum means when the current is minimum, so we'll call that is primary minimum current. When the primary current is maximum, along with the maximum secondary current, reflected current, there will also some magnetizing current is also added, right? So I'll call this one as IP max. So IP minimum, the minimum primary current is equal to the secondary current reflected IS minimum dash. IS minimum dash. Okay, this is normal, right? But when the primary current is maximum, along with the secondary maximum current reflected, plus there will also peak value, maximum peak current of magnetization current is also be added. So these are the values. Okay, these are the different formulas that we have incorporated with this. Okay, we'll stop this here and we will continue in the next.